I've not done anything yet. Cool. So this talk is on a concept. It's not mine. It's not new, but it's called wireless pivots. So that is the act of, I guess you could call it hitting a brick wall, right? So first up, my name's Toby. I've been pen testing since 2012, so around 13 years. I run my own training company where I love Wi-Fi, I teach Wi-Fi, I presented Wi-Fi like 2 days ago, and it's went really well, right? I've got a couple certifications, and I've got a couple of CVEs to my name. So this talk is from my personal experience. It's not about any one specific client, and every story that I tell has something I've seen in the real world, may or may not be modified a little bit. And these are my personal views and not those of any past or my current employer. So if some stories sound familiar, I promise you it's just a coincidence. So a wireless pivot, what is a wireless pivot? So a wireless pivot, think of you've come across a secure client. Doesn't happen often, but you come to this client site, they tell you their Wi-Fi is secure, and they're running EAP-TLS. They've done it perfectly. Yeah. So what can you do? So this talk is about exploiting the neglected security boundary. But first, it's really important that we understand how and Wi-Fi actually works. So here we have the state machine. So you have 4 states. You have states 1, 2, and 3. Those are used with open and web encrypted networks, which you should hopefully never see again. And state 4 is only used with WPA. So in state 1, you're sending what's known as probe requests. Probe requests are networks, requests for networks that you have seen at some point in the past and connected to. Doesn't matter how long ago it was, it will always be asked for, like, hey, Karen, are you there? It doesn't matter. If you connected once, it's always listening. It's always requesting for your ex-partner. So the first hypothetical scenario, right? You have your dream/nightmare client. They've deployed EAP-TLS. That's the only thing they do, and they've done everything right. They have an internal certificate authority, so they're signing everything by themselves. They've deployed the EAP-TLS properly, so each server and client has a public and private key pair, and it's perfect. So what do? Most pen testers would say, job done. It's secure, I can't do anything. And they would maybe issue a zero finding report. So what I want to do is set out what you want to do next. So generally So generally what you do is you would arrive on client site before anyone's there. So like 7 a.m. and you'd set up your rogue AP mimicking the client's network. You would download Let's Encrypt certificates specifically for a domain you control, because when you're verifying a certificate on Wi-Fi, you're verifying the certificate, not where it came from. And next bit, you've got a really cocky client who says, you're going to lose. That's the ideal scenario. So what happens generally is any client will quickly go through to state 3, which is after probe, association, and authentication. They will then go into state 4. State 4 is unique to WPA networks, and in this case, they're using EAP-TLS. So EAP-TLS is the gateway to state 4 for network access. So don't know if you can see it, but this is a very sort of detailed, I guess, view of the EAP-TLS flow. First, you have the states 1 to 3 taking part. So on the left, you have the client. In the middle, you have the access point. And on the right-hand side, you have the back-end authentication server, the radius server. So you set up your data link tunnel, which is going to be your states 1 to 3. And going into state 4, it's going to do this ePOL start, where it's going to say it's going to start a secure connection, right? You then have this identity request. This is where your machine or your device will send something so the backend radius server can identify you, so it identifies you. You then have so that is anonymous, that can be changed. There is a setting in Windows that says enable identity privacy, which is exactly what you want there, right? You then have public-private key pairs. So think of SSH public key authentication. If you're familiar with that, that's how it works. But otherwise, it's basically proving you have access to the private key by sending your public key, and gets really complex. And there's a lot more to this, but that's kind of the bits you need to know for that one. So there's some more steps, but if it's done right, it's perfect. It's the best thing we've got. So what did we forget? What's forgotten? We're talking about mobile devices, right? We're not talking about desktops, which are hardwired. They don't move. We're talking about laptops. We're talking about devices that people can move around. They take these laptops home with them. And like I said before, if they've ever connected to a network, it will always look for that network, no matter where it is. So in essence, what I'm saying is I have never seen a corporate network outside of a corporate business before. Like, if you're working from home, your business is not going to set up their corporate network at your house. So you are connecting to another network. So you work from home, people connect to their own Wi-Fi network. That new network is now saved because they've connected to it. That network is now trusted because it's got its own network profile. You've entered your password, or whatever, it's trusted, right? That is the main important part. So what does this mean? It means that even an unprotected network, say, in this instance, I'm using the name Kathy, right? Kathy is a non-tech savvy employee for this company. She goes home and uses an open encrypted? No encrypted Wi-Fi network, just open. But that network is now trusted, which is really, doesn't happen often, but it can and does happen. So day 2, you go back to the office, right? You find out they've got fast transition enabled. So fast transition is a mode where you generally have multiple APs throughout your building, and you can hop from one side of the office to the other side with minimal latency. It does this by having, basically, fast transition allows you to roam across the office without any sort of disruption. But because that's enabled, your device is looking. It's always searching for a stronger signal, because when you're moving from that side of the office to that side, you don't want to be on that signal. You want to be on the one that's stronger. So you're always looking for a better signal. But you're also searching for trusted SSIDs, which are any network you've ever connected to, which is where it gets fun. So as the attacker, what we would do is we would listen with a monitor mode adapter. We'd listen for these probe requests. Let's say you're probing for your home network, a default ISP router. You set up Rogue, and you change your country code to Bolivia, right? Because Bolivia kind of has lack Wi-Fi laws, which means you can just boost power. You can sort of transmit stronger to hopefully make your signal stronger than the legitimate access points near you. So what happens here is the client who sees their home network, right, will automatically connect to us. But come on, that's old. That's open. Let's be a bit more modern. Let's use WPA2 personal, which is what probably 90% of you are running at home, right? So we're going to set a random random password, and we're going to use the same SSID as before. We're still going to use Bolivia because that's my favorite country. And we're going to run Rogue again. This time, we're going to get the client's going to connect to us. It's going to fail. It's going to say possible pre-share key mismatch. And this is very exciting for two reasons, right? So the device saw us. It trusted us. It trusted the SSID, and it automatically started to authenticate with us using what's known as the mutual pre-shared key handshake. So let's break down why that's exciting to us, right? Hopefully you can see this, but you have the supplicant, the client, and then you have the access point or the authenticator. What they do is the access point will send a S-nonce to the client, so some stuff, right? The client will then use its pairwise master key to say, yes, I prove I have the key. Here it is, and puts a message integrity check. The access point then does some math. It then sends some proofs to the client that it knows the same pre-shared key. And the M4 state is essentially the client saying, all good, I trust you. So in recap, the first two frames, the M1 and the M2, prove that the client knows the pre-shared key. The M3 and M4 is where the access point proves to the client that it knows the same pre-shared key. So the client is telling the AP, I know the key. That's all we need, right? So, well, no, it's not. So the M1 and M2 contain the hash material for the pre-shared key. But it's not enough because the hash is salted. So what is the salt? The salt is the SSID. So you've got the password hash, which is salted with the SSID, which is contained in every sort of beacon frame, including your probe, beacon, association, all those frames. So that's not exactly hard to get. So now we've got the hash, we've got the salt, we just don't know the complexity and the length of the password. So another hypothetical scenario, you've got the default SSID. Let's say you're using the default password set by your ISP. And let's just imagine it's like 8 characters, just numbers, because that's easy. We've got the hash type, which is going to be mode 22,000 in hashcat. We've got a simple NVIDIA H100 series card. Should take around 7 hours to do all, 10,000? Brute force 10,000 numbers, right? So about 7 hours. And as an attacker, time is on our side. You know, as a company that doesn't change, as a user, you don't generally change your SSID or password, but as a company, you might do that. But time's on our side because this is a home user. This is their home network. So we relaunch Rogue, our Rogue access point software. We use the newly correct password that the client was trying to authenticate with. We say this is the access point password. We then use a ---- internet flag and just say, yes, internet, you're at home, right? And the client joined us again. But this time, the client isn't saying, oh, this is wrong. The client is like, oh, I'm at home. I'm on a trusted network again because I've got a stronger signal. So client's on our network, and we've just turned this Wi-Fi job into what's known as an internal assessment. So what we can do as an attacker is attack the client itself, attack the client device rather than the infrastructure. So we port scan the client device, everything's blocked. You know, nmap everything, it's all blocked. But then outbound traffic is enabled because no one blocks that, right? You see local link, multi-namecast resolution, you see MDNS, you see NetBIOS traffic, all multicast, unicast traffic. So you run responder like any good pen tester would do. They'd run responder when you see this stuff, and all of a sudden you'll start collecting NetEnslem2 version 2 hashes. So we're going to get onto hash cracking. And hashcat is my tool of choice. So with NetEnslem v2, I think the mode is 5500, maybe 5600. It's been a while. And we'll have our word list of choice, which mine generally is RockU because it's quick and it's quite reliable. And if not, there's the RockU 2024, which is substantially bigger, but a lot more up to date. So what are the next steps? The client uses EAP-TLS. Client, public private key authentication. They don't allow us anything else. So we cannot use any creds that we get from this to auth to their wireless, which is kind of what we wanted in the first place. We can't plug into the network because we are pen testers outside the building, right? But everything's moving to cloud, which means they've probably got Azure AD, right? So if you can use those credentials for Azure AD, that might be a win. Or they might use Office 365 and things like that. You've got Office. You've got Office.com. If they haven't enabled things like multi-factor, you've just logged in, right? You've now got Outlook Web Access for the internal company. And yes, there's public folders in Outlook. And yes, I have seen clients use public folders for their file storage before. Long time ago, but it was a great job. So in conclusion on that one, to break EAP-TLS, it's really quite simple. Don't use it. As an attacker, don't just avoid. If EAP-TLS is there, just do everything in your power to make the client not use it in any way possible. And I kind of want to move testing away from the wireless infrastructure to be more of endpoint focus, so attacking the device rather than the network. It's the secure network it's already connected to. So that's scenario one. Scenario two. So your client is implementing a brand new bring your own device Wi-Fi network, which is protected with a captive portal, but is like open, so anybody can connect. Just scroll to the bottom, tick the box, yes, I approve, and you've got internet access. It only allows HTTP and DNS traffic, and it's separate in every way. It's got a separate IP space to the corporate. All is good. So what's the vulnerability here? You go to Google, what's my IP address? You have the same IP from corporate as you do on the BYOD, which can only mean one thing, is that the BYOD network and the corporate LAN are sharing the same WAN link to the public internet. So my question, what does a router do? It routes traffic, right? So as you may or may not see, but there is a network diagram there. It's a bit hard to see, but so you've got the wireless on the left, bottom left. Yeah, bottom left. You've got the corporate on the right-hand side. You've got the router in the middle, which is sort of the WAN link to the public internet. And because of that any rule, which allows stuff from any location, from any address to any address, we can use the router as actually our pivot point, which means we can then pivot into the internal network using the router if we happen to know the IP space, the IP range that anything on that network is using. So the exploit. We're allowed HTTP traffic into corporate from their guest Wi-Fi. We're allowing DNS traffic, so we can query their DNS servers. We can query anything running HTTP, but we cannot get SMB. So we cannot do, we can't do responder. We can't do all these exciting tricks to get us creds. But they've got network printers, right? Printers generally have a web interface on port 80. They also have hard drives which store frequently printed jobs on those hard drives. You may or may not be able to access them from the web interface, but they also do network shares. And if you can do a network share out, maybe you can win on that way. Yep, source of contents of previous paint jobs and scanners, sorts of stuff. So in conclusion, bit quick, but thank you for listening to my talk. Wi-Fi is a passion of mine. I hope this somewhat inspires you to think slightly differently when it comes to your next pen test job, rather than focusing on the infrastructure, which is you configure it once and it's perfectly secure versus the client, which has to be configured for every single device where things can go wrong. And I taught Wi-Fi like 2 days ago at the conference, so if you missed it, there's a QR code, there's a link to the recording, and yes, thank you very much.
I am a super genius.